Good evening, everybody. So today we have a talk on the Kaggle competition, harmful brain activity classification. Dmitry Rudenko will present an introduction to this competition. Thank you very much, Dmitry, that you agreed to make a talk, and please start.
Yeah, I'm Dmitry Rudenko, and today we are talking about Kaggle competition about EEG signals. So the goal of competition is to figure out if human's brain works properly, we have 27 gigabytes of data. Mainly it's EEGs and spectrograms. First thing is a raw signal collected from special device, and the second one is just a visualization of it. Usually the spectrograms are used for convolutional networks and such things, VAT transformers, to figure out what works better or worse. But you're not limited of using visual perception. You can build your own transformer model or anything you would like to. Even generalized linear models, as neuroscientists do. For sure. Yes, I can have a little talk about myself. I'm Dmitry Rudenko. I'm kind of 1,200 in global Kaggle rating. I'm not competition master. I'm competition expert. I've got 2 silvers and 3 bronzes. So I'm just solving Kaggle. Trying my best and want to build a better community of Kagglers and competitors. Let's get back to the competition. Here we have not that much amount of patients, only 900.5, but we have several recordings for every patient, so it's a level of granulation for our recordings, and every spectrogram is split it into several windows, and every window is marked up, even by several specialists. The problem of detecting harmful activities of brain is that you have to teach someone to do it properly, and this process is very costly and very perception incentive. So we cannot make persons sit for 8 hours and just look at the spectrograms and sign up diagnoses. Persons have to spend a real amount of time and check it properly several times. So at our competition, every EEG window, such as which is shown to the specialist, is annotated several times. That's why we have KL divergence, as a competition metric. We will get there back. So EEGs is signals from special electrodes located on head of patient, and we have frequency of just a second.
Dima, sorry, you are muted, and please unmute.
Okay, I got it.
Please repeat some.
Yeah, sure, for sure. We have 200 signals per second from every from the whole device, and 50 seconds for every recording. So it sounds like we have a 10,000 lens signal, which is interconnected for sure, because, for example, electrodes F4 and F8 are correlated, as FP2 and F4, for example. So the challenge is to distinguish these correlations, nivellate it, and figure out how do specialists understand the difference between these harmful activities of brain.
So in this picture, what is it? The electrodes, the positions of the electrodes in the brain, or what?
Not in the brain, but on the scalp.
On the scalp. Okay.
Yes. So this there's a special head with a lot of wires, and you put it on, provides some transmitting liquid on your head to transmit electricity better, and that's how you get like recordings. You just always gather the signal from every part of this electrode head.
And will you show us what is the data? It's image or signal? You'll discuss it later.
Yes, it's EEG, so it's mainly signals, but organizers done some work for us and provided some spectrogram images, but we'll discuss some tricks about it a little bit later. Let's stick back to the KL divergence.
Just a moment, there is a question in the chat. It's already cleaned or raw noisy data in the original competition dataset?
It's never clean data at Kaggle. You always have to do some stuff and check out if it's clean or not. Assume it's not clean. It's never clean.
Okay.
For sure, there are some discretization errors, because that's an electronic device which is not perfect. And that's non-invasive measurement. So if we could measure electricity activity of our brain without invasion, Elon Musk wouldn't even try to torture these monkeys in his lab. So KL divergence. Every time window is several time annotated. Our examples in train set can overlap, so we can, for example, have 50 first seconds to be annotated as seizures, and next 20 seconds with overlap of 30 seconds of first example to be annotated with a different label. So for every window, several specialists worked on it, and you have to estimate the KL divergence. So every specialist can have different opinion, and we cannot even figure out which harmful activity is it. We just need to like modulate the work of the specialists. They have some bias towards seizures, they have some biases towards delta signals, and we need to figure out what is more likely to be on a picture or signal. So KL divergence is a non-symmetric measure of closeness for distributions. For example, here you can see, let's assume Px is our predictions and Qx is our ground truth. So measuring KL divergence is to find the integral of non-agreement between these two divergences. So as low as the scale divergence is, the better result you get on the leaderboard at the private leaderboard too. I checked out forum for a while and yeah, we have a question like if minimizing KL divergence is the same as maximizing cross entropy. It's not, as far as cross entropy is symmetric and KL divergence is not. So we cannot say that these two metrics are the same. KL divergence is a little bit more accurate and have a different prior. No, have you plotted the KL divergence with dummy predictors and how does it behave? No, I didn't. But you can like address previous picture and figure out that you can try to, what's the cursor? You can switch the places of Px and Qx and have a different result of minimization than in cross entropy. Yeah, it's better to read a little about KL divergence. That's not hard metric to understand. That's a close into cross entropy, but different one. So Kagglers did some testing, some hypotheses, and figured out a lot of interesting findings. For example, for this test data, there are even more nonce than we have in train. So get rid of nonce or do some job with it, because you have to, because it's kernel competition and your predictions will be scored in online setting. Another finding is that mean number of spectrograms and EEGs per patient are kind of same for EEGs for train and test set, but for test set there are a lot less spectrograms that at the train. Yes, data doesn't overlap. It's separated, I believe, by patients, not by EEGs or even windows. So don't try to map it all together until you have some evidence about data being non-naturally generated. Another great finding which Georgi Borisenko found is that authors provided us not the best way of spectrogramming. As Chris Dale did, he provided his own MEL spectrograms which perform better, and MEL spectrogram transformation have some hyperparameters. So try tuning it. Finding the best way to transform EEGs to spectrograms is a key scene for at least your ensemble. You can try some so the idea of MEL spectrograms is to change the distribution and provide oh, that's a hard word to find out. Transformation without back transformation. So MEL spectrograms concentrate on frequencies human ear can hear and pushes down the modality of sounds you cannot hear. As far as its EEGs, this basic MEL spectrogram hyperparameters doesn't work. So you have to invent something better. And the proof of concept you can find on a Kaggle forum. And that's the idea. Right now, as far as we have 2 months, you first need to set up validational schema and schema of data transformation, working with nonce, working with spectrograms and EEGs. And only after that, you need to figure out which model works better. And yeah, that's it. Does KL divergence penalize hardly for wrong predictions, or we just have to be focused on the good predictions? KL divergence measures not the right or wrong predictions. KL divergence measures the distance between distributions. As far as we have several votes for every example, we want to figure out which examples do we have. Like we want to generate the best distribution. So basically, there are no right answers. That's soft labels and distribution of answers. So yeah, we can go forward and ask other questions. Tried my best to help you understand it. We can also discuss the harmful activities, because I have no, what other spectrogram generation tools have false used so far? Has anyone used multityper? I haven't seen anyone using multityper, but I would suggest starting with fast Fourier transforms and time window fast Fourier transforms, as far as that's a nice and working decomposition for such type of signals. De facto, that's a standard, easy to play tool. I believe there are a lot of data for EEGs and articles, how to measure it better and so on. It might help you as in any medical competition. For example, at UBC, I'm trying to get discussed only state-of-the-art, finding state-of-the-art article was a key to win something. But yep, we cannot find best hyperparameters analytically. I also would suggest trying different decompositions, as far as we have not that much data. Let's get back to that slide. We only have 7,000 unique EEGs, so that's kind of small task even if we will treat every example as 10,000 features, it's not too much. We need first to make data dense and then set up our classifier. Convolutions work nice, but it's not the gold solution, not the thing you would win with, at least not only with convolutions.
Colleagues, okay, so you are welcome to ask questions or comments or suggestions. So maybe I'll try to, you can unmute yourself. Let us try it. I hope there is no Zoom bombers. If there are, then we'll mute everybody again. But okay, so now it's up to you. You can write the question in the chat, or you can unmute yourself. Don't hesitate. And any comments, suggestions, questions, whatever. If someone wants to share his own experience, I see that Arslan is seems to be very kind of profound in this. So Arslan, if you can make any comments, you are very welcome.
I could try, but I'm not sure if I could add much more. I think the presenter did a very great job. Some of the things that I would just recommend doing is that you definitely should subsample your data. You shouldn't work on the entire 200 hertz frequencies because it's 27 gigabytes of data, like you said. So if you subsample it to 50 hertz, so 1/4 of the original 200 hertz, that would significantly reduce the data that you're working with. Plus, most of the events that you will be trying to identify in your EEG, they are definitely not higher than 50 hertz. And if you take into account the Nyquist frequency, then yeah. So I would highly recommend trying to subsample your data. And wavelet convolutions do a really great job. They are used a lot in neuroscience. MEL spectrograms, not really. I think, like you said, they are much more suitable for higher frequencies like audio data.
I also found out, scrolling through the forums, that there is a special course of neuro-EEG science at Udemy, as also wrote in a reasonable price. But I'm not sure.
Probably my discussion. It probably was in my discussion, but yeah, it was 10 euro, I guess.
Could be. So we have. Would you recommend this course? Have you checked it out?
I did it. I completed it because I need it for my PhD, but it would take you around 40 hours to complete it. Probably don't try to complete it fully, but if you would do, then you would know everything that a neuroscientist would need to know to analyze the EEG data. Plus, a lot of things are redundant in that course.
Sounds like I've got something to do while waiting for my Kaggle GPU, like counting something, and at least 2 weeks of it really measures the length of course.
Yeah, but one thing, that course is in MATLAB, as far as I remember, so yeah, you would need to do exercises in MATLAB. So if you're not familiar, it might be somewhat hard to follow along.
You mentioned that you've got PhD with a similar project. What would you say about the organizational process and data, and how much data have we got? Can we find some external data for pre-training, for example?
I think there were a couple of data sets, a couple of EEG data sets on Kaggle, but in general, if you want to pre-train, there is this open repository, Open Neuro. Just Google Open Neuro, and there are a lot of different data sets.
So we believe it's possible to find other data in the similar frequency and use it for like external validation or just for pre-training?
Well, similar, I doubt, but you could do some pre-training on some already existing data sets, that's for sure. And
For
your
example?
best resort would be OpenNeuro. I would write in the chat the exact link. It's openneuro.org.
Would you say it's more pre-training on same data without labels in a self-supervised manner, for example?
Yeah, and then just do some transfer learning. Just train, because it would be very hard to find exactly the same task. So in EEG, usually what subjects, or like you said, patients are doing, they're always involved in some sort of experimental task. I doubt that there is an identical data set that is not exactly this one available somewhere. So just follow whatever the data is giving you, just retrain it. Maybe there are two conditions. You could do some binary classification on two conditions. And yeah, and do some transfer learning afterwards.
Yeah, I just found it beneficial for UBC competition that there were no such a data set as they had, but there were some data set with overlapping classes, and these data sets were a nice boost for everyone. People used or pre-trained models, pre-trained weights for these models, or they used even the data sets to train on them and use competitions data set as a validational set.
That's a bit convolved, I would say. It's yeah, but if it worked out for them, it's really good, but it's too much of an effort.
So as
in my
far as we
opinion.
have not too much patience here, yeah, 2000.
Yeah, but then if you just take the unique, then yes, but so you shouldn't take the unique EEGs like in the Chris Diotta notebook. It's a good idea as a starter, but then at the very end, because it's hard to explain on words, but usually how it happens is that there is this offset time point, and it's very likely that at offset time point 0, one event is happening, and offset time point 2, something else might be happening. So you should crop your EEG based on those offset time points that are given for the spectrograms and for the EEGs. And thus you should increase your data set like that. It's only 1950 patients, yeah, but then you have a lot of data. So at 200 Hertz, you have 10,000 time points for 30 seconds. So basically we should crop the data based on offset time points. It would take a long time to train the model. I tried to do it. It took like the estimated ETA was around, I don't know, 30 hours to train it. But if you downsample your data to 50 Hertz, that should be much quicker.
Okay, at least we can try downsampling the data for like quick experiments and quick iteration, and at the very end, try the full data training.
Yeah, maybe like save 20% of data, try to subsample it, train it on, and also train on all the channels, because I saw in some of the public notebooks, also in Chris Diotta notebook, you only take several channels. Yeah, and one final thing that I would recommend is take the ECG channel separately, because like how we do it in neuroscience, you never treat the ECG channels the way you treat the EEG channel, because ECG is completely different, and you should do some feature engineering on that. And yeah, I could share my discussion thingy here in the comments. You could follow.
For sure, go on. I also forgot to mention that not only brain is covered with electrodes. One electrode is placed on the heart, so it might be very different with all other electrodes. I wanted to ask you the following question. Does your PhD experience gives us some intuition that models tend to overfit for a patient, and everyone's brain activity is kind of unique in local manner, or it never goes that deep, and models never overfit for an exact patient.
Well, there are some problematic patients. How you deal with it in neuroscience generally, during the recording, you can already say that the EEG recording didn't work out. So how we do that, we just remove those subjects from the analysis whatsoever, because the data is unusable. And I saw some of the subjects. Well, first of all, in most of the subjects, in almost every subject, at least one EEG channel is noisy. So you need to deal with it. If you just plot the EEG channels together, the scale for some of the channels, by channels, I mean the EEG channels, they are absolutely on a different scale. So you need to normalize your data beforehand. And secondly, if there are some problematic subjects or patients, you also need to find a way how to deal with it. Usually we just remove those and don't work with them. But here, since you have somewhat limited data, I wouldn't remove the subjects, but I would try to find out something. Like bandpass filtering would work. It's also another thing. I would write it down.
Okay, thanks for insight. Yeah, it reminds me my university days when I went to mathematical methods of prediction at Moscow State University, and they were like experiment. I was like a patient for it, and yeah, electrodes for sure were providing only delta signals. So there might be some problems with connectivity, and yeah, there might be some problematic patients cause devices not used properly.
I see. Maybe just on that note, with Samuel, we were planning to do a similar talk to this one, but you were faster. So if everyone is interested, maybe in a coming week or coming weeks, we could announce that as well. And I will share a couple of more things in addition to what you already shared. If everyone interested, if at least a couple of people are interested, I would be happy to do that.
Yeah, it would be great, because from my perspective, without practical experience, you can't manually filter wrong patients or channels, because you don't know what is right and what is wrong.
Yeah, that's right. So
Yeah,
there's
maybe you can share these notebooks and discussion posts and just go through them and comment. If you have a time, it's okay. I mean, is it possible?
sure. It's
I mean, maybe.
Can I share my screen?
Yeah, Dim, can you then stop sharing, please?
Yeah, for sure. You can stop recording. I believe we have finished, and having a like
I
question
don't mind
and
generally. If
discussion
you want
time.
to record it,
Just
it's fine.
okay. Okay. So, can you share, Arslan? Oh, it's
I
coming.
hope you could see it.
Yeah.
1 second.
It's not a full window, as far as I understand. Maybe you can. Oops. No.
How about now?
It's let's see. It's a rectangular, but not taken.
That's strange. I could share just my entire screen.
Maybe, yeah, try it like this.
How about now?
Okay, no, we can see. Yes, we can see. Maybe not. Yeah.
Yeah, that's fine.
Is everyone seeing the same, or you guys see the entire image? The entire screen even?
This is good. I see your point of view.
Okay. So yeah, I would highly recommend, of course, if you have some extra months, this is like, if I remember it correctly, it's like, yeah, 600 pages book, but everything you need to know about the EEG, it's in here from 0 to hero, basically. But if you don't have that time, there is, by the same author, Mike X. Cohen, you could just follow his Udacity. I think it costs 10 euro or so. It's extremely valuable for that price, to be honest. If you don't want to spend any money, you could, of course, watch some excerpts on YouTube from that course. It will give you some basics of understanding how to deal with EG data, how to compute your own spectrograms, that kind of stuff. What's the difference between Welsh spectrogram, wavelet convolution, STFT, FTFT, and all that kind of stuff. One thing, I tried to use it in my own experiments with this competition. So there is a mini package for the analysis of EG data. But if you're quite familiar how to implement it in raw Python or in SciPy, you don't need to use the mini package, because just importing the parquets into a mini package and then doing something takes a lot of time. So it was not useful for me. There is filter package, which I wouldn't recommend using, but what I would recommend is to use their tutorial, because they explain it really nicely. You could just go, and there are a lot of topics, there are tutorials, and they explain it in a very clear fashion. So for example, of course, this is MATLAB, but you could see what they're doing and what they're using, and they're comparing this multi-tapers, Hanning taper, and all that kind of stuff. You would know what's the difference. Also the Morley wavelets, they're also explained nicely here. With regards to ECG, 1 second. So you could do a lot of stuff. ECG is actually, you could extract a lot of information from it. I wouldn't recommend immediately jumping into computing all of these different features, but start from something small. Try to identify these R peaks, and then compute the R to R interval and feed it into some XGBoost or CANboost or whichever you prefer. Some libraries for doing that are also listed here in my discussion. And also feel free to upload, that would be highly appreciated. So yeah, that's how I would approach. I haven't explored this part. I haven't worked like explicitly with ECG yet, because I was trying to fix my pipeline in TensorFlow. But yeah, if you already solved it, then go ahead and try to figure out how to work with the ECG channel separately. I think that's it.
Thank you very much.
Hey, Arslan, thank you so much. I have a quick question. Sorry to interrupt. So
Sure.
I'm also a neuroscientist, but I don't do any EEG, so I'm learning all of this for the first time. I'm kind of curious about signal and noise in EEG and how to find the relevant sources of noise. And I'm just kind of curious, one outside the box thought I had about EKG was to calibrate the EKG to the EEG and remove any sorts of like noise that could come from that. Is this a potential source of noise or like calibration point that we can use?
Honestly, I would answer your question in a moment, but honestly, I would not try to clean the data, because in this competition, if you just go to overview, there are 5 videos, how like it's basically hands-on how the experts were trying to label different parts. And I saw that they were dealing with non-clean data. So I assume if you're trying to model the experts and their knowledge, you should try to work with the raw unclean data. So the only cleaning that I would try to do is the filtering and the downsampling. But with regards to ECG, yeah, honestly, it's yeah, I'm just giving my opinion, and I see it's being recorded, but EEG is a very subjective field. So as many EEG labs are there, that many people would tell that exactly their pipeline is the most correct. So yes, there are some people, there are some labs that are using ECG in order to find independent components in your EEG data and try to clean based on that. But in this competition, I would not try to do it. Of course, it's a good thing to try it, but I would suggest against it, because I would not clean this data. And yeah, it's very noisy, to be honest.
Okay, thank you so much. I appreciate it.
Sure.
Any other questions, suggestions, comments, whatever?
I would suggest everyone to share their contacts in discussion, because okay, the collaboration with Kaggle might be very, very rewarding and useful for having some medal, right? And prizes also.
Yeah, for example, people might be looking for teams or whatever. If you are kind of open
You hear me?
for the team, you are. Mikhail, you have a question?
Yeah. As far as I know, the most success right now in the competition is are made on spectrograms that are made from authors of competition, and just applied some ResNet neural nets to it, and it's like top 50 leadership right now. Am I clear?
Yep, you are clear. And yeah, as I said, that's not the most effective way of doing it. But applying convolutional neural networks, even for vision, for these MEL spectrograms, are common sense approach. It's mastered at Kaggle, I don't know, million times, so it's okay to do it. But you need to figure out which spectrogramming is the best, and yeah, also try not using spectrograms but raw signals.
Okay, thank you.
You never know which approach will win.
Good.
Hey, I have a quick question. So I've been following a lot of what the experts are doing, like Chris, but I think we all know that in order to win this competition, we'll have to do something much more creative. And so far, what I've seen is using convolutional neural networks to analyze spectrograms. And I'm just kind of curious what other sorts of thoughts or like general ideas people have in order to increase diversity in our models and maybe not only rely on convolutional neural nets.
So main part of the competition main part of participants will stick to the public kernels, and as experience shows, public kernels are merely the shadow of diversity of top solutions. So I would suggest trying your best of building some, I don't know, Fourier fast transformational based model for all this recording. At least you will be able to blend it with the top solutions and get better results than them. There are also challenges to figure out the way of augmenting the data, because usually people use like random flips and noise and so on, which could be not that effective in terms of our data. So augmenting using non-standard approach, just distantiate from public kernels, is the key to get something better than public kernels.
Yeah, I'm trying my best to add some other augmentations. Like I've done some Gaussian blur, contrast, and brightness sorts of augmentations with varying success. It's very slow because it takes so long for the GPU. But yeah, I'm open to suggestions for augmentation.
I would suggest using PyTorch with two augmentations, which are kind of fast and they are fully made on GPU. So it's kind of state of the art at this moment. They really improved the thing. And another thing I would think could work is transforming the signal from raw signal to spectrograms and applying augmentations right to the raw signal. Like you can add some noise, which will be non-equally augmented into MEL spectrogram. When you augment MEL spectrogram, it's already spoiled with some noise and transformations, but augmenting raw signal might be beneficial.
Yeah, that's a great idea. Thanks.
Aslan, maybe there was a question that what's your look? What's kind of your what do you think you'll do in this competition? If it's not a secret, just
No, of course not. I tried a couple of different things, but during training I was receiving nonce out of nowhere. But what I would recommend doing is that maybe some multi-headed neural network with multiple inputs could be a good point of experimenting. Something like WaveNet on one end, where you just feed in the raw EEG time series and the convolutional layer would just convolve along the channels. On the other hand, you would have some conv2D model, and then at the very end, you concatenate the outputs, and then you try to put it together. So that was my plan. I tried, I failed, and then gave up for a while to come up with better ideas. But that's how I would approach it.
thank you very much. We have another from Alexander. I'm not sure. So this is more kind of suggestion. Oh, sorry, Arseny. Arseny, you can, if you want, you can unmute yourself and speak it out if it's convenient, or I can read it.
Sure, just blend in. You've got a very deep thoughts, and it's better to explain them.
Yeah, so, but sometimes people are unable to unmute. So, okay, Arseny, if you're able to unmute, please, any moment, but I'll start reading. So, Arseny suggests to denoise using the reference electrode. Functional connectomes for small time step windows. For serious graphs, for each patient, you can extract a lot of interesting features. From TDA, is it topological data analysis maybe, or spectral graph measures, features used in any machine learning algorithm. Okay, so okay, if anyone can comment on this, you're welcome. There is Arslan then writes, do you know each from the neuromatch? Arseny says yes. And Shane says, I was thinking about doing neuromatch. That's awesome. Guys, what is neuromatch? What are you talking about?
Yeah, it's popular summer school, as far as I know, for neuroscientists, computational neuroscientists.
Ah, I see. Okay. Okay. Okay, Arslan shares the link. And this for free. Okay, thank you. So I'll post all the links to the Kaggle forum. So I'll copy them. Any other comments, suggestions? Okay, colleagues, any more questions, comments, suggestions, whatever? Maybe just a few short questions. So the current kernels, do they optimize this scale divergence?
Yes, current kernels do optimize scale divergence. They also tried cross entropy, and cross entropy works worse. So scale divergence is a loss for distribution optimization, and it works perfectly.
But I've seen that Chris mentioned something like cut boost, but in cut boost, do you have this scale divergence?
It's not that hard to differentiate it, and yeah, cut boost might have scale divergence even for multi-class. but I believe not for GPU as they do.
Okay, okay. Dmitry, can you please share the screen again with your presentation? I have a couple of questions on the.
Yep, for sure I can. I have screened. Was Stalker and Arslan to team up, but yeah, we can get back there. Yep, let's go. Which slide?
Okay. Can you explain a little more on this? What is the difference between spectrogram and unique EEG ID?
So spectrogram is a recording, full recording of person. It can be, I don't know, 2 minutes long, 10 minutes long, very long. But EEG ID is a sample we want to predict. That's a time window of 50 seconds to be shown for a specialist and being labeled by him. So,
sorry, but does it mean that we have this 17,089 labels? Is it correct?
no, we have even more labels, but we have 17,000 objects. Labeled,
and each object is labeled by something like 6 experts or many experts
or less or more. Yes, but mean number of experts is 6, kind of 6.
Okay, okay. So just again, so this period which expert is labeling is 10 seconds or 30 seconds?
50 seconds, 50.
50, okay, 50 seconds. Okay, and they are labeling by their kind of experience, domain knowledge. They just look, or I mean, we don't know exactly, yeah, but
yeah, they just look at the picture and mark it up. They say like, okay, that's hard delta magnitude. It might be latent delta disorder, or how is it called? I don't remember.
So what is the correspondence? So we have something like about 2,000 patients and 11,000 spectrograms. That means something like 5 spectrograms for patients. Something
Yeah,
like
for
that.
sure. Yes, yes.
Okay. And so we have 17,000 is labeled periods. Does it mean that we have for each spectrogram something like 2 periods, two fragments which are labeled? No, maybe not 2, but 1.5 something. I mean, in average.
Yes, all this. Okay, some labeled windows are overlapping. It can be used for training for sure.
Okay. And just again, so spectrogram is a time series, yes?
Yes.
And what is the granularity? Each second, each, I don't know, millisecond? Or...
Each second we have 200 signals.
Each second we have 200 signals.
Yes.
And this is from each electrode, and because we have...
Yes, from each electrode.
Okay.
We can get somewhere there. No, we cannot. So it was another picture. I haven't added it. But yes, we have 20 electrodes and 10,000 measurements for each.
So, and this is the kind of main input data, yes? The time series is. And
that's it, yes.
What is the average kind of how many seconds they are?
50.
I thought that 50 is labeled periods, but spectrogram I thought is long.
I got it. Spectrograms could have different lengths. So like there is distribution, and we don't need to work with spectrograms. We just need this like periods of 50 seconds, which are labeled.
But why? There seems to be some feature which we can use, no?
Sorry?
No, why it seems natural to use all the spectrogram? No?
Yes, I got it. People do not have this harmful activity all the time.
Mm,
Imagine, as a very rude example, epilepsy.
okay.
When people have a seizure of epilepsy, their brain do not work properly. But all other time, people are okay. They even can take their pills to like treat epilepsy and live better life.
Mhm. And these labels, they also come 200 labels per second, or it's just
Yes.
one?
Okay, not. The label is provided for the whole window. So, for example, we have 50 seconds, and all 50 seconds have the same label, but we have several labels, so they are normalized.
Okay, I see. Can you go to the next slide, please? No, next. This one. So, what does it mean? Shapes of the EEG are 20 by 10,000. It is
Yes.
20 because this 20 electrodes, including this on the heart, or?
Yes, 20 electrodes, 50 seconds, 200 recordings per second.
Okay. Shapes of spectrum.
May I ask you,
Yeah,
Yes,
sure.
guys, I've already wrote it in the chat. Is it correctly, I mean, from the medical point of view, if we will add additional data from the healthy patients, because as I understood in this competition, we get data only from the patients who are in the intensive therapy, and I just assume that it's totally different kind of EEG which we got from the people who are the healthy, or who are just switched off from their body and lie in the intensive therapy.
As far as I see, we have a class which is called other. So we can put healthy patients to other to like build better feature extractor. So yeah, for external data, we can boost it up. It might work. No one knows if it will, but it might work.
And what is shapes of spectrograms? I thought spectrogram is longer, but you said it's.
So yes, spectrograms have like some hyperparameters of transformation. That's why it's not one-to-one transformation, but spectrograms are like denser.
But spectrograms is something which was computed by the organizers from this EEG data, yes?
From the raw EEG data, yeah.
Okay. And on forum, there is suggestion that maybe we can do better, something, yeah.
For sure we can, at least for some neural networks, people achieved better result just by pre-processing.
Okay. And these neural networks, what is the input for them? The spectrograms or the EEG? So someone is training on EEG, or everybody using the spectrograms?
Everyone is using spectrograms because it's easier, and you just can like throw your convolutional neural network and believe in better.
Okay. And when you say convolutional neural network, this is one-dimensional because it's a signal, or it's a kind of somehow.
No, 20 dimensions.
Oh, okay. But
10,000
just a moment. Why 20? Then it should be 300, no?
when you use raw signals, there are 20 electrodes.
But you say that people are using spectrograms, not EEG.
Yeah, I got it. Yes, people use 1D neural networks, but it's not the state of the art right now. But for sure, it might have performance.
Okay.
So that's another idea to blend with.
Yeah. And so the 2.5% is less than mean ratio of none in test spectrogram.
But there are some.
So there are some nuns in spectrograms.
Yes.
I don't quite understand. But are there nuns in EEG also, or?
Yes, there
Okay.
are no nuns in EEG data in test, but in train you have some, but not too much.
Okay.
For example, one electrode gone dead or something.
Okay. And 5 less than mean number of spectrogram EEG per patient makes it 6 mean number of spectrogram. Oh, yeah, okay, that's understand. There are no lots. Okay. Okay, Dmitry, what's your plan? If it's not a secret, just what kind of approaches you think you can try? If it's not a secret, I mean.
I'm dreaming of building a strong transformer-based model with a small size, as people usually do in the recent competitions. At least they are getting interesting results. Not the best, but I believe it might improve my hard skills. But for sure, it will be clear what to do at the very end of the competition, but I won't have enough time as usual. So we'll see what happens. I really like this competition. It's not too big, it's not too small. And
27 gigabyte, it's not too big.
It's not too big.
27 gigabyte.
A previous competition I was participating in, which was UBC, had 700.
Wow. For me, it's too big. But what is current experience? Do people do some ensembling blends? Does it help, or what's that?
Yes, for sure. It always helps because you have diversity in your model and some unknown parts of distribution in your test set just is not that well generalized.
Well, the trick we should discuss in the chat, take different random seeds and average random seeds. Does it work or not in this?
It's not only about the random seeds. Every model has its own optimization space, and if you have the same architecture of model with different random seeds, it still has the same optimizational space. That's why you never know which model will be the best one for the task.
Yeah, but I mean, sometimes there is a kind of top model and all the others, they do not give much. And sometimes you need to make, I don't know, 20 models. And so what is the situation here? Is it 1 or 20, I don't know, 100 something?
Yes, and that competition is great because it doesn't have a obvious solution. It's obvious you need to use a convolutional neural network for ImageNet classification or like VIT transformer. But here, you are free to try literally everything.
Okay. colleagues, any other questions?
Yeah, I have a brief comment about spectrograms that it's really an art to make spectrograms from raw signals. So you have different ways to do it, and even if you do it different way, you can use it for blending and sampling, just other types of spectrograms that you can prepare. So yeah, it's there are no silver bullets for AG data, and it's great that we have this competition to know what works best.
And have you looked at the public notebooks, Mikhail? Are there already kind of many spectrogram methods presented, or you suggest that there can be plenty more that we should try something? Or
The best public notebooks, it's ensemble of two models. As far as I know, they both use the same spectrograms from authors, and it's one of the model. It's public baseline from top one leaderboard. It's just so it's a lot of ways to make something better than.
okay. And also, I think in this public notebooks that the people are using WaveNet, something like that. This is something like a pre-trained model on some signals. So
I have seen ResNet, EG. Oh no, I have seen ResNet, EfficientNet. I have heard from neuroscientists about AGNet, but I haven't seen it in computation yet.
WaveNet is a 1D convolutional based neural network. So it's just an architecture, and it might work as far as we have signal. WaveNet is usually used for text to speech, or at least speech to text.
Maybe we can discuss some day later these architectures or something.
Yeah, we can do it. If you have a will for it, we can organize it.
I would happy to.
Yeah, I will happy if you kind of will have time to kind of share experience on this.
Yeah, I'm not sure I can host it as a speaker next week, but I will check out my best. And if someone wills to, it's a great pleasure to hear from you.
Yeah, in general, colleagues, so we organize kind of data science, and some of them on Kaggle, some just this kind of webinars quite often, and we are very happy if someone will make a webinar, will share his experience. So we are quite informal. You don't need to be, I don't know, super Kaggle grandmaster or whatever. Just if you have something which you think that is interesting, you like to share, you are welcome. Okay. Okay, thank you very much. Any other questions, comments, suggestions, whatever? Okay, if no, then Samuel, any comments?
No, just thank you for the organizing.
You're welcome. Okay, so thank you very much, Dmitry. Thank you very much, all the participants, Arslan and all the Mikhail and everybody. So have a good evening. So the video recording will be on our YouTube channel, I hope tomorrow. And the link will be on Kaggle forum. Okay, so thank you very much and goodbye.